Greetings, everyone. Thank you for taking time out of your day to be present for our presentation. Today, we're going to be presenting our final project for our statistics and probability class with the title Statistical Look at BMI by Gender. I'm going to introduce the members of our group. Let me introduce myself first. My name is Emily McGardian Dexter.
My name is Kesia Fania Dwi Payana.
And my name is Limadia Putra Anggita.
Okay, next. Project overview. Before we start, let's go into the project overview. This project involves collecting a sample of data and applying statistical analysis techniques using the R programming language. With the help of Google Colab, we calculate descriptive statistics of the data, create data visualizations of the data, and execute several hypothesis testing tests on the data. The findings are then analyzed. Table of contents. First, we will go into data collection, where we'll be going over our process of collecting the data needed for a project. The second is descriptive statistics, where we'll be going over the descriptive statistics of our data made and presented by me. The third is data visualization, where we'll be going over the data visualization of the data we have collected, made and presented by Kesia. And lastly, the fourth, hypothesis testing. We'll be going over the data hypothesis testing with our language using Google Colab, presented by Angita. The first section, data collection. The data collection method is a questionnaire. We use a Google form as an instrument to help us spread the questions, allowing people to easily respond. The data we collected from respondents were the gender, age, body height, and body weight. Our main goal in this project was to calculate the responders' BMI values. It was done using the Google form link below. The thing that we focused on our project was BMI. What is BMI? BMI stands for Body Mass Index, which is a measure of body fat based on height and weight that applies to men and women, where the formula is weight in kilograms divided by height in meters squared. Now for our documentation. This was the Google form that we made and we shared to respondents. This is the 10th of December when we've got our first 20 respondents at 6:09 p.m. And this is our last documentation where we decided to stop. On 11th December, 9:35 p.m., we got 40 respondents, where we got an equal amount of 20 males and 20 females. Our sampling method. The sampling method we used was convenience sampling, where convenience sampling is a non-probability sampling method where units are selected for inclusion in the sample because they're the easiest for the researcher to access. The easy way we used is sharing the form link widely, using social media and WhatsApp groups to anyone who would respond. Convenience sampling is a type of non-random sampling. Sometimes it is called accidental sampling. Now onto the next section, section 2, descriptive statistics. The first step was to input the data into R. As you can see, first we inputted the male's height, and I inputted them individually. Next is the male's weight. And then after that, under the variable male, we put in the BMI formula, which is the weight divided by height squared. And then we did the same for females. And then that resulted into the BMI data table on this slide. As you can see, all the respondents' BMI are presented in front of us. So going into the commands for this project, for descriptive statistics, specifically the male category. The first, I'll be explaining the mean. This command calculates the mean or the average BMI value for the male participants. The result is approximately 21.52, which means that on average, male participants in our data have a BMI of around 21.5. This falls within the normal weight range. The second is the median command, which is the middle value, when all BMI scores are arranged in order. So for the males, the median is 20.44, meaning that half of the male participants have a BMI below 20.44 and half have a BMI above it. Since the mean and median are fairly close, it suggests that the BMI data for males is not heavily skewed. Third is the quantile command, where this command gives us the quartiles, the value that divides the data into 4 equal parts. For the males, the 25th percentile, or Q1, is 19.28. The 50th percentile, or Q2, which is also the median, is 20.44. And the 75th percentile, which is Q3, is 23.13. Which means that 50% of the male BMI falls between 19.28 and 23.13. Next is the minimum and the maximum command, or the minimum and maximum values. These commands show the smallest and largest BMI values in our male dataset. The minimum BMI is 16.49, while the maximum BMI is 30.12. The participant with the highest BMI was identified using the command which.max. The result was 18, which means that the 18th male participant in our data table showed previously had the highest BMI in the dataset, with a height of 168 centimeters and a weight of 85 kilograms. Next is the range. This function shows both the minimum and maximum values again, but it helps us understand the overall spread of the data. The BMI values for males range from 16.49 to 30.12, meaning there's a difference of about 13.6 BMI points between the smallest and largest values. Next is the standard deviation and the variance. So these two functions measure how spread out the data is from the mean. The standard deviation for the male group is 3.49, meaning that most BMI values fall within roughly 3.5 points of the average. The variance command, which is the square of the standard deviation, is 12.17. A moderate standard deviation like this suggests that while most BMIs cluster around the average, there are a few higher or lower values that create some spread in the data. Next is the descriptive statistics for females. I won't be explaining the commands all over again, but I will be presenting the results. So for the mean, it's 22. For the median, it's 21.25. And the quantiles for 25% is 19.8. 50% is 21.3. And the 75% is 24.6. The minimum is 16.35 and the maximum is 29.4. And for the which.max is the 18th data, and the range is between 16.35 and 21.4. The standard deviation is 3.6 and the variance is 12.81. Now let's get into combined descriptive and frequency analysis of BMI for both male and female. First is the summary. Using the summary command, we generated a concise statistical overview for both male and female BMI values. For the males, the mean BMI is 21.52, and for females, it's slightly higher at 22.09. The median values also show that females tend to have slightly higher BMIs overall. Both groups have similar minimum values around 16, but the maximums reach around 30 for males and 29 for females. This summary gives us a clear picture of the central tendency and spread before moving into more detailed analysis. Next, moving into row sums and col sums. The row means command calculates the average BMI across genders for each pair of male and female data points. Essentially, it tells us the mean BMI value per observation, combining both male and female values in the same row. Meanwhile, col means command calculates the mean BMI for each gender column, which gives us 21.52 for males and 22.09 for females, confirming the same values as our earlier summary. The core command. The core command is used to check the correlation between male and female BMI values. The result gives us a correlation coefficient, which tells us whether changes in one variable are related to changes in the other. Since the correlation value is close to 0, it means there is no strong linear relationship between male and female BMIs in this data set. Moving on to categorizing BMI, or the cut command. So using the command below, we group BMI values into standard categories: underweight, normal, overweight, and obese. So for example, any BMI under 18.5 is classified as underweight, 18.5 to 24.9 is classified as normal, 25 to 29.9 is overweight, and anything above 30 is obese. In the frequency table, using the table function, we calculated the frequency of participants in each BMI category. Among males, most participants, 12 out of 20 to be exact, fall into the normal range, while one participant is classified as obese. For the females, 12 are also in the normal range, but 5 are overweight, and none of them are obese. This gives us a clearer picture of how BMI categories are distributed between genders. Next is the marginal totals, or the margin.table command. The margin.table function calculates totals for rows and columns in our two-way table. For example, margin.table tab 1, 1 gives the totals for the male categories with 4 underweight, 12 normal, 3 overweight, and 1 obese. Margin.table tab 1, 2 does the same for female categories, with 3 underweight, 12 normal, and 5 overweight. These totals confirm our earlier frequency results. Lastly, we move on to proportions, or the prop.table. Prop.table command is used to convert the frequency values into proportions or percentages. The first command, prop.table tab 1, gives the overall proportions. Prop.table tab 1, 1 shows row proportions, or the proportion of female categories within each male category. Prop.table tab 1, 2 gives column proportions, or how each male category contributes to each female category. These help describe the relative distribution of BMI categories across genders. Though, since these are not paired samples, we have to interpret them cautiously. That is all from my section. We will move on to Kasia's section.
Now we will move on to data visualization. So here, there will be charts and graphs involved, and the BMI data visualization was created in R. Before we execute the code to create data visualization, we first need to create the code for data preparation. And the code are as follows. First, we will discuss about the scatter plot. So here, the plot function in R creates a scatter plot for two variables. We choose the male height for the x-axis and male weight for the y-axis. We create main title called scatter plot and subtitle below the plot called height versus weight. We choose the color for male points is blue and plotting character is 19. And here sets the x-axis range from 145 to 190 in the scatter plot and set the y-axis range from 40 to 95. Then we add points for the female data. We make the shape of the point with triangles filled with the color red. For the legend, I created the legend to be on the top left with the text size of 1.2. I give it the title legend, and in that legend, there will be two lines. The first line is male with PCH19 filled with the color blue next to it. And the second line is the text female with PCH17 filled with color red next to it. Now let us observe the graph. Now if we observe this graph, we can see that as height increases, the weight generally increases. And this happens for both genders. This is showing that there's positive correlation between height and weight for both genders. And as you can see for the female data, the part here is more clustered than the male ones, especially at the mid-range heights. The male data have greater spread in weight, especially at taller heights. Now we will move on to scatter plot, but this one is with regression line. In this scatter plot with regression lines, the code is basically the same as the previous code, but here we add appline function. So appline function in R is used to add one or more straight lines to a graph. And we will use the LM function in R, which is used to fit linear models to data frames in R language. After that, we make the line width equals to 2, and we use the color deep sea blue for the male ones, and we use the color hot pink for the female one. As for the legend, we can add legend for male regression line and female regression line, and then we can create the PCH line style and line width. And here NA means no point, meanwhile and here NA means no line. Now here is the graph. So this regression line confirms what we were visually suggesting in the earlier scatter plot. There's positive correlation between height and weight. The male regression has positive slope. The female regression line also has a positive slope. But as you can see, the female regression line has a steeper slope than the male ones. This indicates that weight increases more rapidly with height among females in this data. We'll move on to the histogram for the male ones. So his function in R computes a histogram of the given data values. And in this code, we use the male BMI data. And then we create a main title, which is histogram of male BMI, and assign BMI as label for x-axis, then fill the bars in histogram with the color light blue. Now in this histogram, the x-axis represents body mass index, and the y-axis represents frequency, or the number of males. Now, each bar represents the number of male individuals whose BMI falls within a specific range. This histogram shows that its distribution is unimodal, where there is one main peak. This peak appears around here, indicating that most males in the data falls in this range. There is a central concentration of BMI values in the low 20s, approximately 19 to 22, which appears as two adjacent height bars due to binning. You see, it becomes even clearer if we break it into 15 bars that this histogram's distribution is unimodal. Now back to the previous distribution, we can see that there's a slight right skew. The right tail extends toward higher BMI values. This means that only a small number of males have relatively high BMI. This histogram is approximately bell-shaped, but not perfectly symmetric, and the slight right skew suggests that the data may deviate slightly from normality. And if we observe, there's a data point appearing as isolated, short bar on the right side. This indicates unusual values that deviates from the typical pattern, and this is possibly an outlier. And here is the histogram. Now, prop equals to true tells R to plot probability densities instead of frequencies. And the lines function is used to add new lines to an existing plot, and density function to compute a smooth density curve estimated from the data distribution. Line width equals to 2 with the color light blue 4. Just like our analysis before, this histogram distribution is approximately bell-shaped, but not quite symmetric. Bell-shaped means normal distribution, so this BMI distribution is approximately normally distributed. Now we will move on to the histogram for female ones. This code constructs a histogram using female BMI, and it displays main title histogram of female BMI with each bar filled with color pink. The highest frequencies are around BMI equals to 18 to 22, suggesting that this is where most female BMI values fall. This range corresponds roughly to the normal BMI category. The BMI values ranges approximately from 16 to 30. This indicates a moderate spread covering underweight, normal, and overweight categories. Now, this is the histogram with a density curve. The shape of the distribution is approximately bell-shaped, and as you can see, there is a slight positive skew as the right tail extends a bit further than the left. The peak of the histogram and density curve is around BMI equals to 19 to 21. Visually, this data does not show any strong skewness or extreme outliers. Now we will move on to the box plot. First, we need to combine two factors, namely male BMI and female BMI, as columns into a matrix called BMI data. The box plot function automatically detects that BMI data has two columns, and it creates separate box plot for each column. We give names to the box plot and add a main title, which is box plot of BMI by gender. We can use separate colors for each box plot, and here I use Dodger Blue 1 for male and Fire Brick 1 for female. I also added gender label for the x-axis and BMI label for the y-axis. As we have predicted earlier when observing the histogram, there is one high outlier on the male BMI box plot. Now, if we compare the female BMI median, the female BMI median is slightly higher than the male BMI median. This indicates that on average, females in this sample tend to have a higher BMI than males. And it is meaning that most likely the mean of female BMI is greater than the mean of the male BMI. The female BMI also shows a wider interquartile range, meaning that there's greater variability among females. Meanwhile, male BMI distribution is more compact and less variation. Both males and females have similar minimum BMI values, which is around 16 to 17. The maximum BMI is higher for females, extending to close 29 to 30, while males reach about 27. Now we will move on to the bar plot male. Using the cut function, we divide continuous numeric variable, which is male BMI, into categorical groups or intervals. We are dividing in according to weight categories using BMI values. Now intervals become underweight are the BMI values under the 18.5, and then the healthy weight ranges from 18.5 to less than 25. The overweight is from 25 to less than 30. The class 1 obesity is from 30 to less than 35. The class 2 obesity is from 35 to less than 40, and the class 3 obesity is equal to or greater than 40. And by using the table function, we are counting individuals per category. It basically converts the factor to frequencies. The bar plot function creates a bar plot using the weight categories data. Then we set the main title as male BMI categories and label y-axis as frequency. Then we assign different colors for each bar, which I have made it to vary around the blue color. And less equal to 2 to rotate the x-axis label vertically so it can be read clearly. And I set the CAX to 0.7 to prevent overlaps. We can see that the healthy weight category has the highest frequency, indicating that majority of males in the sample fall within normal BMI range. Some males under the category of underweight. A small number of males are classified as overweight. Class 1 obesity is rare, and Class 2 and Class 3 obesity are absent, meaning there's no males falls into the higher risk categories. Now we will move on to bar plot female. This code works nearly the same as the previous code. The only difference is it uses the female BMI data. So it categorizes female BMI and individually counts per category, then it creates a bar plot for it. And here I made the color of the bars around red to orange. Now again, the healthy weight category has the highest frequency. This shows that the majority of the males in the sample fall within the normal BMI range. A small number of males are classified as underweight, and a moderate number of females falls into the overweight category, and no females are classified as class 1, class 2, or class 3 obesity. Now we will move on to the pie chart for the male one, and here we need to prepare weight categories like in the bar plot male BMI code. But now there's this line. What is this? The use of this line. So you see, some BMI categories may have 0 individuals. And as we have seen in the previous bar plot, class 2 and class 3 obesity are absent. So pie charts should not include zero-sided slice because they cause overlapping levels and cluttered visuals. So this line keeps only categories that actually appear in the data. We can create a color palette. This line generates a color vector with exactly 1 color per BMI category. Start and end restrict the rainbow to be around the blue colors. The pie function in R is used to create a pie chart. We use weight categories as numeric frequencies that determines the sizes of each slice. And we set the main title as male BMI categories. The color equals to pie colors, and clockwise equals to true. The clockwise equals to true means the slices are drawn clockwise. Now the legend is placed on bottom left. It uses BMI category name as legend labels. Colored squares filled with colors in accordance with pie slices colors are displayed. And BTY equals to Y to draw a box around the legend, and CX equal to 0.9 to slightly reduce the legend text size for readability. As you can see, the healthy weight covers the largest portion of the pie chart. Smaller portions are classified as underweight or overweight, and there's only small proportion for class 1 obesity and none for class 2 or class 3 obesity. Now there's pie chart for the female one. This code works nearly the same as the previous code, and the only difference is in color settings and the fact that this code uses the female BMI data. This pie chart shows that most females are of healthy weight, while a considerable proportion are overweight and a smaller proportion are underweight. No obesity is observed in the female sample. Next, we'll move on to the line chart. This code creates a line chart using plot function. We use male BMI data and set BMI trend as main title, then set individual index as x-axis label and BMI as y-axis label. Type equals to O, meaning we plot both lines and points. Line width equals to 2, PCH equal to 16, solid circular points, and color equals to 4, which is blue. Afterwards, we need to add the female BMI as a line with line width equals to 2 and color is 2, which is red. And lastly, female BMI points with PCH equals to 16 and color red. As for the legend, we can place it on top left with labels male BMI, female BMI, color blue and red, PCH equal to 16, line style 1, and line width 2. Both male and female BMI values fluctuate across individuals. That is why there's no clear trend across the index, but we can see that the highest point in the male group is higher than the highest point in the female group, meaning that maximum BMI value in the male group is greater than the maximum BMI value in the female group. Now we'll move on to the QQ plot for the male one. QQ norm function creates a normal QQ plot for the male BMI. Meanwhile, the QQ line function adds a line to the QQ plot to compare the distribution of the dataset against a theoretical distribution. Now we can see that most points lie close to the reference line, especially in the center. This indicates that the male BMI data are approximately normally distributed. The lower tail shows a small deviation from the line. The upper tail has a few points slightly above the line, suggesting a mild right skew. For outliers, there exists one high value point that stands out slightly. This corresponds to the outlier we found back in the box plot. We'll move on to the QQ plot for female. This QQ plot can be created using the code QQ norm function and QQ line function. And if we observe in this graph, most data points lie closely to the reference line, particularly in the middle of the distribution. This suggests that the female data are also approximately normally distributed. There are only slight deviation at the tails, and overall, there's no indication of serious deviation from normal distribution. For the next part will be explained by my friend.
All right, thank you, Kezia. We move to hypothesis testing. Testing hypothesis of the data using our language through Google Colab. So what is hypothesis testing? Hypothesis testing is a method in statistics for making decision or drawing conclusion about a population based on sample data. Uh, there are two kinds of them. Null hypothesis. This is the starting assumption that there is no effect or no difference. And alternative hypothesis. This is the hypothesis that contradicts the null, suggesting there is an effect or difference. Next. So we jump into type error. There's two kinds of type error. Type 1 error happens when you reject the null hypothesis, even though it's actually true. In simple terms, you think you found an effect when this is also called a false positive. In reality, there isn't one. The probability of committing a type 1 error is denoted by alpha, which is the significance level you choose for your test. And then type 2. Type 2 error happens when you fail to reject the null hypothesis, even though it is actually false. In other words, there is a real effect, but your test didn't detect it. This is also called a false negative. The probability of the type 2 error is denoted by beta. The power of the test, its ability to detect a real effect, is 1 minus beta. Next. So this is the example. The example for type 1 error, imagine a medical test for a disease. If the test says a healthy person has disease, that's a type 1 error. You incorrectly detected a disease that isn't there. Type 2 error. In the same medical test, if a sick person tests negative showing they don't have the disease when they actually do, that's a type 2 error. Next. So we move to type of sample tests. There's three kind of them. So number one sample t-test. A one sample t-test is a statistical hypothesis test used to determine whether the mean of a single sample is significantly different from a known or hypothesized population mean when the population standard deviation is unknown. Number two, independent two sample t-test. An independent two-sample t-test is a statistical hypothesis test used to compare the means of two separate groups to see if they are statistically different from each other. The key idea is that the two groups are independent. The data in one group doesn't affect or come from the same subject as the other group. Lastly, dependent two-sample t-test. A dependent two-sample t-test, also known as a paired t-test, is a statistical method used to compare the means of two related groups to see if they are significantly different. It is used when the sum participants or units are measured twice under two different conditions or at two different times. Next. So it's time to testing our data that already collected. So first of all, we need to read the study case. Researcher will compare the average BMI value of two groups which are classified by genders. Suppose that the test will be conducted between the male and female groups. The initial hypothesis states that there is no difference in the average BMI values of male group and female group. The alternative hypothesis is that the average BMI values of male group and female group result in different average group rates. In short, we need to test it whether the men and women have different average BMI value. Next. So before we testing, we need to do preparation. But before we do the preparation, need to recall what is BMI. BMI is body mass index, is a number used to estimate the relationship between a person's body weight and height. So as you can see on the screen, there's BMI formula to calculate. So we need back to the preparation. Number one, you must have list of height in centimeter and weight in kilogram for two group, male and female. So these values are used to calculate BMI for each person. After you calculate BMI for each individual, These values are stored in a data table and can be used for further statistical tests such as normality tests, variance tests, and t-tests. Next. So we now do the first task, which is Shapiro test, to check whether the sample of the data comes from normal distribution or not. Next. So, as I said before, we use our language on Google Colab. So this is the formula of separate tasks and the result below. For the male BMI data, as you can see, W equals 0.93, and p-value equals 0.223. So the W is the test statistic value. Since p-value greater than 0.05, we fail to reject the null hypothesis. This means there is no significant evidence that the BMI values for the male group deviate from a normal distribution at the 5% significance level. Next. For the female BMI data, the W equals 0.95, the test statistic value, and p-value equals 0.50. Again, p-value greater than 0.05, so we fail to reject. There is no significant evidence that the BMI values for the female group deviate from a normal distribution at the 5% level. Next. So we next do the FAR test. The FAR test function performs as an F-test to compare the variances of two samples. Here, the BMI values of males versus female, it tests null hypothesis, the variances of the two groups are equal. Alternative hypothesis, the variances are not equal. This test assumes both groups come from normally distributed populations, which you already confirmed earlier with the Shapiro-Wilk test. Next. So as you can see on the screen, there's a formula and the result below. For the F statistic, if variances were exactly equal, this ratio would be 1. Your value is close to 1, meaning the sample variances are similar. Next. For p-value, this is the probability of observing a ratio at least as extreme as the one you observe, if in reality the variances are equal. So 0.991 greater than 0.05, we fail to reject the null hypothesis. This means there is no statistically significant difference between the variances of BMI in males and females at the 5% significant level. In simple terms, the variation or spread of BMI values in the male group is not significantly different from the variation in the female group. Next. So, 95% confidence in interval from 0.37 to 2.39. This interval is for the true ratio of population variances. Because this interval includes 1, it supports the conclusion that variances could be equal. Ratio of variances 0.94. This is the observed ratio of variances in your sample. Again, close to 1, reinforcing that the variances are similar. Next, we have Bartlett test. This is a Bartlett test for checking whether the variances of BMI are the same between males and females. The p-value equals 0.991 is much larger than 0.05. Because p-value greater than 0.05, we fail to reject the null hypothesis. The conclusion is there is no significant difference in the variances of BMI between the male and female groups. In other words, the BMI values for both genders appear to have equal variances or homogeneous. Next. Finally, we arrive to t-test. This is a two-sample t-test to check whether the average BMI of females and males is different. The p-value equals 0.61 is much larger than 0.05. Because p-value is greater than 0.05, we fail to reject the null hypothesis. The conclusion is there is no statistically significant differences in the average BMI between the female and male group. In other words, the average BMI values for both genders appear to be not significantly different.
Now, here the member contribution details are as follows. The one who created the Google form is everyone in this group, and the one who spread the Google form link is also everyone in this group. The one who worked on the descriptive statistic is Emily. The one who worked on data visualization is me. And the one who worked on hypothesis testing is Angita. And the one who created this PowerPoint is everyone in this group. So thank you for your time and attention. We apologize if there were any mistakes. So thank you very much.